gigantic pain in the ass for dual citizens like Carla.
Yep.
All right, we should be going live in a second. We are theoretically live. I got a piece of content recommendation. Queen's Gambit. Have you seen this yet on
No,
Netflix?
what is it?
It is. It's about this chess prodigy. This woman who's a chess prodigy and sort of starts out as an orphan and then works her way up through the chess world to the highest levels. It was sort of set back in the 1960s during chess frenzy, and it's really good. It's really good.
Okay.
It sort of does a really good job of showing like chess nerdery at its finest, like to the level that like today we have people are into video games or Harry Potter or whatever.
Yeah.
Back in the day, they didn't have video games. You could just watch a television show, and then if you wanted to watch it again, that was just too bad,
Yeah.
right?
Yeah. No, that's true.
Yeah, you could watch a movie a few times if you wanted to, but yeah. So chess was like video games, was the World of Warcraft of the 1960s, and it's just amazing to see people just playing this game obsessively, talking about it. There were magazines, people were reading about it, and it's really well timed too because there is like there's a big chess revival happening right now on Twitch and stuff, right? Everyone's totally into chess again, so
Yeah.
it's pretty great. And so Carl and I watched it. We loved it. Logan, like independent, was like, "Dad, have you watched this show?" I'm like, "Yeah, we're almost done." He's like, "Yeah, it's really good." And then my dad emails me and goes, "Here's a good show for you." So
Oh, jeez.
yeah, yeah,
Okay. I
yeah.
will
And
add
so
it to the list.
I've mentioned this before that I really love, and so it's just based on a book from the 1980s, I think. And I just love this idea of just really good books getting picked up by Netflix or Prime or whatever,
Yes.
being adapted into a series, but that's just one time, takes as long as it takes, like maybe it's 4 episodes, maybe it's 8 episodes, however
Yeah.
many episodes it is, to tell the story right, and then it's over.
Mm-hmm.
It's the greatest. Like I don't need 15 episodes of CSI Las Vegas. I don't need
Yeah.
another sequel to I don't know, to some superhero movie. I want to see interesting stories told, and the more of this, the better. People are asking about the Hangout-a-thon. How did it go?
It went really well. So our goals were to build a scale model of the solar system and raise money for CosmoQuest. And we were able to raise just over $14,000, and we completed most of the solar system. It turns out that a sphere that is 256 blocks in diameter takes a long time to paint. So Saturn and Jupiter are still in the process of being fleshed out, but everything else got put in, including a bunch of Easter eggs. On the Earth side of everything, there's a VAB, there's a Starliner, there's a whole bunch of cool stuff. We're going to keep the server up and running through US Thanksgiving, maybe a little bit longer. And we're going to make it available for download once we're done with Jupiter and Saturn.
Right. How big were like Earth and stuff to scale? No.
Everything, no, we did everything entirely to scale. The separations were to the exact same
Right?
scale as the sizes of the objects. The definition was Jupiter was 256 blocks in diameter because that's the maximum height you can do in
Mm-hmm.
Minecraft.
Mm-hmm.
And the solar system at that scale, we were able to get out as far as the um, Kuiper Belt object Iris. And
Wow.
unfortunately, at that point, we ran out of blocks. We didn't try and make the sun to scale. Instead, the Welcome Center in space was the nucleosynthesis portion of the core of the sun that you landed upon.
The You ran out of space? Like a lot of blocks? Like I don't understand how that works. Weren't you in creative mode? Can't you just make as many blocks as you need?
Right, the distance in blocks, not the number of blocks that you can use to paint things, put
Yeah.
things, build things. So a Minecraft world is, I want to say, 3 million blocks in all directions
Okay,
in the
I thought it
XY
was
plane.
unlimited just based on your
No,
memory. Maybe it used to be that, and then they put some kind of constraint in it because I think it
now you
used.
can have so much memory. Yeah, no,
Yeah,
there's a constraint on it.
yeah. Um, but how could you put the VAB on a Earth?
So the way that we did this was when you spawn into the game, you're in the regular part of the world.
Okay, I see.
And then we put space in the end. So um, you essentially have two dimensions that you can play with
That's
in
cool.
Minecraft. And we used one to build the solar system and another to build basically a rocket park that includes the VAB.
Yeah, that's really cool. I don't think anybody's done this. Built a
Now,
scale model of the solar system in Minecraft. No, that's pretty
mo-
impressive.
most people, they don't, they either have only the worlds to scale and not the
Yeah,
separations, or they just do things willy-nilly. And we're like, no, we'll put teleportation stations between the worlds,
yeah.
and it's kind of awesome.
That is amazing. Well, congratulations on putting yourself through 36 hours of streaming. You took a couple of naps though, right?
So we are a team. I streamed 27 of those 36
Wow.
hours. And my co host, Annie Wilson,
Yep.
along with Ms. Brickkitten and Beth Johnson, and a bunch of other members of our community, held the overnight hours. And
For
as
science.
we got through it. And if you didn't tune in and you didn't donate, it's plague times, it's an election year. We knew we weren't going to hit our fundraising goal because the economy is hurting right
Yeah,
now.
yeah.
If you're someone who can look at your retirement savings and be confused that the stock market is continuing to boom, we could use some more help.
Right.
Go to cosmoquest.org and help us support our staff in putting together all the content we do. We provide full medical benefits to any of our part-time staff who need them because plague times, and we're
Hmm.
going to keep doing that forever and always. But it means that it costs real money to do all the things we do.
Yep. Well, people are mentioning you're a machine. So thank you from everyone out there for your dedication. I know I mentioned that in the stream for the couple of times you had me, but you just are rocking this whole
Thank you.
process. You, no matter what comes your way, you step up to the challenge and demonstrate your commitment to science and science communication and getting people involved in helping us understand the world. So thank you. And I'm
Well, I
sure it'll
have
happen
great people to
next year.
support me.
Yeah, well,
People like you make
well,
this possible.
but that's the thing. You feel responsible. Like I find
Yeah.
it's funny. Like when the virus hit at Universe Today, I scaled up my team. So we've actually got probably 3 or 4 extra writers now.
Mm-hmm.
I've had to spread things around a little bit, but
Yeah.
I just said like, how can I hire more people
Yeah.
to because people were hurting. I saw a
Yeah.
ton of newspapers went under, a bunch of journalists were looking for work, and you're like, okay, what can we do to try to give people work? It's a
Yeah.
tough time, and
Yeah.
so I think it's great that you're just stepping up to the challenge and proceeding. Okay, we should do this thing that we do, which is
So before we do it, I want to explain. My heat is out. So if I'm sitting here looking bleary
mhm.
and shivery as I am wrapped in a wool blanket, it is because it is all the expletives cold. We are going to attempt to replace the igniter on our gas boiler. I live in a historic house, which means finding someone to do it is a challenge.
Right.
So apologies for looking bleary and cold. I am.
Maybe it's time for a heat pump.
I don't know how we would even install one in this house.
I would get a quote. They're pretty amazing, and they're relatively inexpensive these days. You need multiple emitters across the house, but I'll bet you It'll
We
save
would
you
need
cost.
air ducts, and we don't have those.
No, they don't need air ducts anymore. They're called ductless heat pumps. It's a whole new
Okay.
world out there now. Yeah, you should definitely check it out. They're way cheaper than they used to be. They don't need ducts. They give you air conditioning in the summertime and heat in the wintertime. And they're pretty amazing. So check it out. Just take a look. Just get
Okay.
someone to give you a
Because
quote.
I live in a historic
I know. I
house.
know. Just
All right.
see.
So we're 580 what on this episode?
I don't know. 584. Let's say
Okay.
584.
Okay. Hopefully we're right. All right. I'm ready to press record.
I am also ready to press record.
I
did
have
it.
pressed record.
Record has been pressed. And hello, Richard Drum. Thank you for agreeing with my system. All right. Astronomy Cast, episode 584, Asteroid Sample Return Missions. Welcome to Astronomy Cast, our weekly facts-based journey through the cosmos, where we help you understand not only what we know, but how we know what we know. I'm Fraser, Cain, publisher of Universe Today. With me, as always, is Dr. Pamela Gay, a senior scientist for the Planetary Science Institute and the director of CosmoQuest. Hey, Pamela, how you doing?
I am cold. Our heat is out. We need to get it fixed. But other than that, life is good.
Yeah, have you recovered from the Hangout-a-thon? Have you had a couple of good night's
I
sleep?
I'm going to definitely sleep in this weekend. Streaming for 36 hours and then going into a full work week is not there will be much sleep this weekend.
Yes. Uh, well, you've earned it. It was you guys did a great job. You built Minecraft. You raised $15,000. If people still want to donate, they can go to cosmoquest.org and contribute to help cover CosmoQuest's expenses, help pay for the salaries of the people involved, including their medical expenses. It's an important work that you're doing, and definitely we all appreciate it. So definitely, if you haven't already, contribute. Or even go watch the Hangout-a-thon. It's all archived until Twitch throws it out. So,
and we will be updating as much as we can onto YouTube. The last hour was an extremely touching memorial to one of our dear friends, and we blew up Bennu.
right.
Which sometimes you just need to do.
Speaking of, let's talk about this week's episode. So with a sample of asteroid Bennu firmly inside of OSIRIS-REx's return capsule, it's time to bring this treasure home, so scientists can study the composition and history of the space rock. But it's not the only sample return mission out there, with Japan's Hayabusa 2 mission also bringing asteroid debris home. So today, let's talk about the missions and what we've learned so far. Today we're going to talk about asteroid sample return missions, but it's not just the two. OSIRIS-REx, which we watched launch together,
Yes.
and I separately watched the whole retrieval process happen. There's Hayabusa 2, which is one of my favorite asteroid missions ever, but there was also Hayabusa 1.
Which I have to admit is the mission I continually forget about, even though it was a mission that was just like, okay, problem, gonna overcome it. Okay, problem, gonna overcome that. Oh, another one, gonna overcome that. And they just had to keep figuring out ways to overcome issues.
Yeah, so let's talk briefly about Hayabusa 1 before we go on to the other missions.
So Hayabusa 1 is a mission that I think part of the reason I keep forgetting it is it came out right after I finished my PhD, and I suspect my brain has blocked most of that year out of existence. It was originally scheduled to launch in 2002. The rocket it was going to use had an issue with a different mission. So they delayed the launch of Hayabusa 1 in order to make sure their rocket was working, and just additional stuff came up along the way. They missed their window for their initial asteroid. They had to go to a different asteroid, but they eventually successfully took off in May 2003 and headed their way out to Itokawa, the asteroid that we really, really thought Bennu would look like. It didn't. It really didn't.
Yeah, I mean, if there's one thing that we've learned from these 3 separate asteroid sample return missions is asteroids don't look similar to each other.
Yeah. Well, unless it's Ryugu and Bennu, in which case they're hard to tell apart unless you look closely. But Itokawa really looks like a cashew that in
Yeah.
a few places has been dipped in granular material. Um, it's a cashew with periodically grainy surface. And the poor spacecraft, though, while it was on its way to the little cashew Itokawa, um, it found itself in the path of the largest solar flare recorded in modern history.
Oh, poor
This
buddy.
this damaged its solar cells, and it ended up with less electrical energy than it planned to have. Then in 2005, two of its reaction wheels failed.
Right. And in fact, the reaction wheels, I think they were the same reaction wheels that were lost on Kepler, and a couple of, like, there was a bad batch of reaction wheels out there.
Mistakes were made.
Yeah, yeah. So okay, so here's the spacecraft hit by a solar flare, down reaction wheels, but it still made it to Itokawa.
It made it to Itokawa. It had a bad dress rehearsal for doing its sample. They finally were able to get there, and they released the Minerva mini probe. It too failed. This,
Yeah.
but they made it. They sent back beautiful, beautiful data. Beautiful data. Um,
And they
yeah,
and they also sent back a sample.
they did.
Yeah, and the first and this is what I love is, they were hoping to bring back hundreds of grams of material, and in the end they were able to bring back just grams, just a couple of
Yeah.
grams, just a few tiny pieces of dust.
So here we're talking about like a dime's worth of material.
Oh,
So it wasn't a lot, but it was a pioneering mission. And after something has been hit by a solar flare, you really need to lower your expectations, people.
yeah.
And the fact that it succeeded at doing anything after getting blasted by that much radiation is really a testament to how well engineered this stuff is, how well shielded this stuff is. Um, it had a bad day and it kept on going, and it returned science. And that's all you can ask for from any space probe,
Mm-hmm.
is to
Mm-hmm.
return science.
So learning from those lessons, the Japanese went back and prepared a second mission.
And what I love is with their second mission, Hayabusa 2, they seem to have taken the approach of, we will take every single little tiny robot we possibly can with it, and
Yeah,
we will fling all of them
yeah,
at
yeah,
the asteroid, all of them at
yeah,
the asteroid, and see what
yeah.
works.
Germany's like, we've got one. Japanese like, no problem, throw it on board. We'll try everything, including
Yeah.
the kitchen sink.
So they had Minerva 2, Mascot, Rover 2. They had cameras on board. They had an anti-tank
Yeah.
weapon that they dropped. They had target markers that they dropped to help them maneuver around. Um, they just kept flinging things at Ryugu,
Hmm.
and then eventually they flung themselves at Ryugu, grabbed a sample, and they grabbed a sample with so much energy that they actually sent the asteroid vibrating, according to a paper that came out just in the past 48 hours.
Yeah. So it's funny. I was going to bring that up as well. We probably both saw this same paper, that the surface, they were actually able to measure after the spacecraft bumped into Ryugu, as well as hitting it with its impactor. They were able to actually detect shifting movements across the surface of Ryugu in response to the damage that they had done from visiting it. So
Yeah.
that alone is going to be very helpful for just getting a sense of like what it might take to be able to move an asteroid in the future if we run across
Yeah.
them, and sort of shows how much they really are rubble piles and not space rocks.
and it shows what Lucy has the potential to do, but there is something making noise in here and I can't reach it. I suspect I'm getting a phone call. Yes, let me decline that. Sorry.
That's
okay.
I always get a phone call during every live stream that I do. I pretty
Yeah.
much now have to have my phone turned off all the
That
time.
was my watch. That's not fair.
No,
I accidentally let its battery go all the way
yeah,
dead,
but
and when it recharged, it came back
yeah,
ringing.
yeah,
Anyways, returning back to this. So, I with Hayabusa 2, it didn't just take a sample, it attacked Ryugu. So it did two different samples. The first one, it went down, and this was a surface sample. It went down and it fired a 5-gram titanium projectile at 300 meters per second into the
sorry,
surface.
titanium.
That's what it is called.
Okay, not titanium. Okay, no problem.
No, I'm sorry. I'm going to make this hard for you to edit, Richard. Um, it's a chemical, atomic number 73.
Okay, very dense. Cool.
Yeah,
I'd never heard of that before.
I had not
Then
either.
you just get to
Thus,
keep Richard. Don't worry about it. Just like pretend like I never questioned her wisdom.
all right. So let me repeat that sentence. So they launched a 5-gram titanium projectile at 300 meters per second into the surface of Ryugu. This allowed them to get a surface sample, the material that was blasted up by the projectile they collected. But they were not content to merely get a surface sample like any other mission would be content to do. No, not at all. Um, they wanted a subsurface sample as well, and this is where that anti-tank weapon came in. They had what was called a small carry-on impactor that carried a 2.5 kilogram copper projectile, which was shot with explosive propellant into the surface of Ryugu, creating a fresh crater
Right.
in the process.
Right. And so, I
Yeah.
mean, that is such a brilliant idea that the surface of the asteroid, okay, great, you grab a quick sample of the surface, but the deeper question is like what does it look like underneath the surface which hasn't been blasted by the sun for billions of years? Will you find volatiles? Will you find water, other interesting samples down deep? And so you need a crater like on Mars, right? The way Curiosity is driving up the side of a crater to, or inside a crater, looking for essentially the history of Mars. Hayabusa 2 wanted to look at a crater, a fresh crater on
So it
Ryugu,
made it.
so it made one. There, crater made.
And
Boom.
the
Take that.
this is this is just insane. So they shot Ryugu from a distance of 500 meters, and the crater they made was 10 meters in diameter, exposing pristine material. And they did a touchdown sampling of this as
Oh,
well.
amazing.
So here they were, February and July 2019, maneuvering their spacecraft to go pick up samples. So they have both fresh and not so fresh
Right.
material that they have collected.
So before we get on to OSIRIS-REx, I just want to just like say again, like if you are excited about interesting missions across the solar system, I highly recommend you follow what the Japanese are
Yes.
doing. They are just incredibly creative and willing to take big risks and try interesting ideas at a fairly shoestring budget to be able to do this. And so Hayabusa is just like the Hayabusa 2 is like the perfect example. It had an ion
Yeah.
engine. It had this anti-tank weapon. It had two methods of doing sample collection. It had three lander rover. It had one thing that just sort of flipped and flopped across the
Yeah.
surface of the asteroid. Like they just the level of creativity and innovation is just so high. And I've even heard interviews with people from the JAXA team that worked on this, and you can just sense this really beautiful balance of wanting to get interesting science, but also wanting to test new ideas, and they're not super concerned if they don't work out right. And obviously it can go horribly wrong with Hayabusa 1, but it can also go incredibly right. And so when you look at their future mission, they've got the Martian Moon Explorer mission coming up to Phobos. You're going to see a version of that where they're going to try all kinds of really clever ideas to study Phobos. And I cannot wait. I think if there's like one future mission that I'm really excited about, it's going to be the MMX. So anyway, stay tuned on that. But anyway, let's so Hayabusa 2 gathered its samples, and now it's bringing them home.
And this is one of the parts of the mission that is most remarkable to me at a gut level. Like, I know mathematically and engineering wise, this should be trivial, but they have run the math so that they depart on time, fly towards Earth, release their sample, flinging it at our planet so that the planet will rotate underneath the sample, and the continent of Australia, in a fairly specific part of the desert, will catch the sample. There's a helicopter involved.
Right.
Will catch the sample from Hayabusa 2. The fact that we can fling things at the Earth from greater than the distance of the moon and know where on the Earth they will hit months ahead of time is just...
Yeah, absolutely incredible.
Yeah.
So Australia, look forward to receiving a sample of an asteroid.
In December of this year. We will bring it to you live on CosmoQuest on Twitch.
All right, but that's 2 asteroid sample return missions. There is a third, OSIRIS-REx.
Yes. And this is the mission that we got to go watch together launch in September of 2016. And this little mission was one that had the youngest NASA PI of a spacecraft to date, Dante Lauretta. It was run by a really cool team of people at the University of Arizona, working in collaboration with international partners, NASA centers, a myriad of other institutions, and Canada had a laser altimeter. The sample they collected is going to end up getting split between the Canadian team with that laser altimeter that we're going to return to because it was not used as planned. The Japanese team that they're going to be doing an exchange between the Ryugu sample that comes back and the Bennu sample that comes back. And then the rest is heading off to Arizona for processing. So in this case, Bennu arrived in December.
You want to say that again? OSIRIS-REx arrived?
Yes, thank you. OSIRIS-REx arrived at Bennu in December of 2018. We began to get our first high-resolution images in 2019, which caused me, for one, to completely panic.
Yeah, well, you have a little skin in the game on this one.
I did. So the CosmoQuest citizen science community was part of the process for mapping out all the hazards on Bennu. Now, as I said before, we expected Bennu to look a bit like Itokawa, mostly smooth with areas that were hazardous. We were expecting most of the images that came back would have a few boulders, a few dozen rocks, and we just mapped things out, no big deal. The reality was each image had dozens of boulders and hundreds of rocks. And all the software that we had written to process everything and sort everything and do everything had to get redone to deal with the complexity of this little world that we found. And making it even worse, as the spacecraft approached Bennu, OSIRIS-REx caught in its camera glints of light from pebbles being flung by Bennu into space. We had found a rock-throwing asteroid.
Right. Yeah, I mean, it's funny when I think it was Dante was saying, the landing site, the final landing site that was chosen, I would not want to land a spacecraft there. Like, it's a nightmare. And yet it was the best possible landing site on a nightmare rock.
Yeah, they had to change their hazard conditions to go from having a area big enough to park a couple semi trucks to having an area big enough to park a couple SUVs as their safety margin.
Right.
And so they had this need to find some place that they could go down, not hit the wings of the spacecraft on anything, and that would be smooth enough that in all likelihood, when their tag instrument, which is a flat disk, hit the surface, it would hit flat and the spacecraft wouldn't tilt more than a few degrees. And it turned out the only places that vaguely matched these conditions were areas that were either craters or craters inside of craters. And these weren't normal looking craters. What these were areas where the rocks were more smashed than the regions around them. And these smashed rocks were in a fairly circular pattern, indicating this is a crater where the rocks there got crushed. Nightingale Crater, where they ended up doing their sample collection, was in the northern part of the asteroid, about 55 degrees latitude. And it was a crater with a few boulders that they had to make sure they didn't hit. And because the surface was so much more complex than anticipated, they had to take a spacecraft that had been planning to maneuver by laser, just like a lot of modern cars will use a laser on the front of the
Right.
car to measure the distance to the car in front of them, and then back off if they need to when they get too close. Canada built this instrument. It was supposed to be the way. They found their way to the surface. Except OSIRIS-REx said, I'm going to be complicated. And what ended up having to be done is they programmed vision into the spacecraft, allowing it to do natural feature mapping
Right.
in real time, autonomously from 18 and a half light minutes away from Earth, so that as the spacecraft is descending, it's taking images, comparing the images to the existing maps. And as long as the area below the spacecraft doesn't go red, they keep proceeding.
Yeah.
But this is not how the spacecraft was designed, and their ability to retroactively add this
Yeah.
powerful feature really says something about their programming and navigation teams.
It was pretty exciting to watch the actual sample collection. It happened like a week ago, and you got this like as it was descending to the surface, and as they were watching it, they were talking about how closely the spacecraft had gotten to their predicted model and how far away it was, and they were also just noting that the spacecraft hadn't abandoned hadn't aborted because it was up to the
Yes.
spacecraft to make this
Yeah.
decision. So it was descending towards the asteroid and going, I think it's still fine.
Yeah.
This is okay, I think. It had tucked in its solar panels and was slowly making its way down to the surface, and it just wasn't making the call to abort, which was amazing.
And it was intended that the spacecraft would touch the surface, fire off a nitrogen canister. NASA took a gentler approach than JAXA. Fire off a nitrogen canister that would then blast dust and small particulate, nothing bigger than 2 centimeters, could fit up through the capture tube. And this nitrogen blast would deploy, and then within 5 seconds, the spacecraft would pull away. Except it turns out the surface of Bennu wasn't exactly a solid surface.
Right.
And so instead of tapping the surface of the world, giving it a nice gentle snoot boop,
Yeah.
where it's the snoot of OSIRIS-REx that's getting booped by Bennu, no, they instead punched the asteroid, going down many centimeters through the
Wow.
surface.
Like I imagine it's sort of like going into snow, right?
Yeah.
Like it dropped its sample capsule into snow or its collection,
Yeah.
vacuum cleaner, and then
Yeah.
did it. And we saw as it successfully captured its sample and started to move away from the asteroid, there was debris coming out of the sample collector.
Yeah, it was said in the images that it looked like someone dumped a box of cornflakes outside of the tag. This is the touch and go sample collection system. And the problem was the way the system was designed is they had this disc. On the outer ring of the disc, there was essentially metal Velcro, little tiny metal hoops designed to pick up dust and debris from the surface in the Velcro. And then in the center, there was an opening that was supposed to have a mylar flap that would slide in like a shutter to close off the collection
Hmm.
tube and make sure that nothing would escape. And a rock, something got jammed in there. And so small material was escaping. It's unknown exactly how much material they got. They were aiming to get roughly 2 ounces, the weight of a C cell battery, and nothing bigger than a C cell battery. That was the goal. Anything bigger just wouldn't have fit into the detector. Um, they don't know how much they got.
Yeah.
They think that it was potentially significantly more. There were originally plans to spin the
Yeah.
spacecraft.
It's such a brilliant idea that how they were going to test how much sample they got. The plan was you lift up, start to rotate the spacecraft around, and you could detect the wobble from the mass inside the collector as compared to what it was without the mass inside the collector. And that would tell you whether you got a good enough sample or not. But they just decided, forget it. We're not going to do this test. We don't want to risk losing this material because we just need to get it inside the capsule and call it a day. Just
They even delayed a braking maneuver they were planning to do to keep themselves in the orbit they meant to be in. It was no acceleration, do nothing that could possibly exert force on the sample and cause any more material to escape than was already escaping. So, several days ahead of plan, in fact, more like a week ahead of plan, they folded the sample collecting head up into its return capsule to bring it home. And this is a super ingenious way that they did it. It had this long arm that it extended with the disc and suction device on the end. And ideally, when they spun it, because it was this long arm, it would be like an ice skater holding a barbell, but a
mhm.
really tiny one. And it just changes the way the spacecraft spins. But then taking that arm, folding it up, and pressing it into a set of latches. So we've all had various devices where you can clip something in, and then when you go to pull it back out, it's like, nah, the clips have gone, and you have to fuss with the clips to get your thing out, but sliding it in is super easy. So they very carefully, over 24 hours, and here they couldn't automate it. They had to see images of every single step in case debris came out, dust got in the way. They needed to have human beings with eyeballs looking at the images coming in
Yeah.
and decide. So they folded the arm, image, folded the arm, more image, touched the tag device down in to the capsule to bring things home, made sure it was fine, clipped it in, pulled up on the arm, made sure it was still fine, disconnected the arm, made sure it was still fine. They worked around the clock with a 37-minute round trip for
Yeah.
every
Oh.
bit of information. And it worked.
Hmm. So now it's going to be coming home.
It's gonna be a little while, so they have to wait for everything to get lined back up. They planned the sampling so that if things didn't go well, if they did have to steer off, they'd have time to try at least 3 more times.
Yeah.
This is why they had 4 potential sites. Well, it worked on the first try, and then they had to speed up their time zone to latch everything in place, protect everything all up in the capsule.
So they got time to kill.
Yeah, so they're going to be there until March. They are now projecting that the orbital alignments and maneuvers will allow them to make it home in September of 2023. And I look forward to all the images that they're going to be able to continue taking, seeing just what they did to the surface at Nightingale. And hopefully, even more science will be made possible from a safe distance.
Right.
From a safe distance.
So when does the sample come home and where will it go?
It's going to go to Utah in September 2024 once the sample is collected from where it gets thrown in Utah. It will get sent down to the Johnson Space Center, where all space samples go,
Right.
and then divvied out to the Canadian, Japanese, and University of Arizona partners.
Fantastic. Well, I cannot wait for all of the samples to come back and for us to finally learn these deep insights about the formation of the solar system, the current environment out there in space, what they're made of. Will they be resources that we can use for the exploration of the solar system? There's so much to learn from these pristine samples. So let's hope they both safely make it back through the Earth's atmosphere. So we've got more than just a couple of grams to analyze of asteroids.
This is true.
All right. Thanks, Pamela. Do you have any
Thank you
names
so
for us
much.
this week?
I do, but then I forgot to open that window. Hold on. Sorry, Richard. I am torturing you. I don't mean to. I apparently opened it on a different screen, which is why I don't have the window. Awkwardness. So the way my setup works is I have a monitor mounted to my desk that I can rotate when I'm sitting in this chair. Anyways, that's too much information. Pardon me while I log on.
We can skip it this week, or
we can, or I can record and add it later because I'm not even logged into the correct account.
We'll do that then. You can.
Okay.
All right. So I said thank you, Pamela. We'll see you next week.
Thank you. See you later.
Okay. Let's save. And then you can decide if you want to do that after the fact. Save.
Yeah, I'll do it afterwards.
Okay. We have people to thank.
We do.
584.
The social media team for OSIRIS-REx had this fabulous tweet of what we were, where we are now.
Right.
And it was quite brilliant.
All right, let's take some questions. Graham W. is asking, I wonder if they found any signs of water on Bennu.
They did find a myriad of different kinds of rocks, including rocks that had to form in hydrated conditions. So they didn't so much find water as they found minerals that required water to form and may have water incorporated in their matrix.
Anti-Gravity Nonsense asks, did they have multiple cameras on OSIRIS-REx to take those pictures, or did they just have one that moves around?
No, they had multiple cameras that each worked in different ways. So they were, as they were making their descent, that was all one camera. And they used different cameras for different parts of the mission to succeed in different tasks, ones that had different zoom rates, that sort of thing.
Right. Hal McKinney asks, and this is a question about spectroscopy, how do you distinguish individual elements and molecules from the single spectral signature of a distant star? Wouldn't the signatures overlap? So when you're doing spectroscopy, how do you know which are the chemicals in that star?
Atoms and molecules are pretty friendly for this one particular task, except for the math you have to do. In a given atom, you have a core with a certain number of protons and neutrons surrounded by electrons that are bound with a very specific energy to that nucleus. And there are a variety of allowable energy levels, quantum energy levels that the electrons can be at. And in order to jump from one energy level to another, the electrons either have to absorb the exact right color of light, the exact right energy photon, or they have to emit the exact right color of light or energy of photon. When we look at the full spectra of a star, spreading the star's rainbow of light out into all of its different colors, we'll see in that light dark bands that represent For instance, all the allowed transitions of hydrogen, all of the allowed transitions of titanium, all the different compositions that can be in a star will have their specific barcode. And all these barcodes are superimposed. And some of the lines do overlap one another, which can get super annoying. But while there's a few that will overlap, most of them will still be free. So while you might be missing one of the 5 lines for this, 5 of the 30 lines for this other thing, the lines that you aren't missing allow you to say very specifically, this is what I have here.
So, I mean, at the time that we're talking right now, the evidence for phosphine on Venus is starting to fall apart. There's been many fairly significant papers by a lot of heavy hitters who know their science questioning the actual detection of phosphine in the first place. Yeah. And that was done with spectroscopy using the ALMA instrument.
One line.
Right.
They used one line.
So that's the problem. And so can you explain that? So you say they have one line. What does that mean exactly?
So when we look at a open sign, this is the thing I constantly return to, a nice bright red open sign at a store or restaurant that may be emitting light in H alpha. This is a bright red color emitted by hydrogen. And it's also emitting a whole bunch of other colors, and we're just not seeing them because that red is the dominant color that our eye is detecting. And in astronomy, we'll often use an H alpha filter when we're looking at nebula, when we're looking at galaxies, and we'll use that single line to diagnose different things about the object. And we sort of assume all the other lines are there, and most of the time that's fine. But when you're just trying to start to make a detection, this can become a bit of a furry mess.
Right.
In this particular case, in the infrared, which is where they were working, I think they were actually in the submillimeter for this one, the wavelength that they were working at, you can't readily get hundreds of wavelengths of light in a single image with ALMA or any of the other radio detectors. You have to tune in, and you can tune over a thin band of different wavelengths, but not the hundreds of lines you might get at once in an optical telescope. So they first, with the Maxwell Clerk telescope in Hawaii, did an observation that had a not very distinct signal, but what appeared to be a signal of phosphine in the atmosphere of Venus. And they said, okay, let's see if we can recreate these observations using the significantly more sensitive detectors on ALMA. Now, with all of these detectors, you have to do certain things while you're processing the data. This is because either effects in the sky, effects in the electronics will cause what you're looking at to not have equal sensitivity across the entire band you're looking at. This is something that many of you are probably seeing with beginning green screeners nowadays, is if you don't have your green screen evenly illuminated, the person will cease to green screen in the corners because of that gradient of light behind them.
Right.
Well, we have to correct for the gradient of light in the sky with optical images. We have to correct for differences in sensitivity in our detector in different places, no matter what instrument we're using. And all of these standard corrections you do, if you screw up anything, you're going to imagine that you're seeing something that isn't there. And ALMA has come out and said that their standard set of software that they use, their standard procedure for reducing ALMA data had an error in it. And that error caused a signature that may not have actually been there.
Oops.
And so now
I hadn't heard about that. I heard them say that they might have an error in their data, in their software.
Yeah.
Oh, wow.
Yeah. So this isn't necessarily a problem of the research team. This is a problem of the telescope team. And the researchers didn't reproduce their data from scratch, which is how the problem was found is a lot of researchers, I'm one of them, are like, I want to do all of my data myself. You may have a pipeline. I deny your pipeline.
Huh.
And so it's this let me do it myself mentality that allowed this problem to rise to the surface. And now there's a lot of debate going on because reprocessing of other data from other missions has potentially found phosphine. And so the question becomes, is phosphine sometimes there? Did the Maxwell Clerk telescope potentially see it? Did this mission potentially see it? And
Right.
ALMA missed it, and new observations are needed. And it's going to be a furry mess for a while.
Yeah.
But it's a tantalizing, scientifically pursued, good to think in detail, and science is working right furry mess.
So is the problem, like, you talked about a star and you said like it's super
Mm-hmm.
easy to detect chemicals in the light of a star. Is that because the
Yeah.
star is giving off the light in the first place, while a planet like Venus is the reflected light from a star?
So it's a two factor problem. So first of all, when you're looking at a star in optical, which is what I was thinking about, our optical telescopes have the ability to spread all the light across all the colors of the rainbow out, and that vast amount, there's going to be strong lines in it that are super super easy to see, and there's also going to be super weak lines that are really hard to see.
Mm-hmm.
Lithium determinations in optical light spectra are something that we're still struggling to consistently to get right because lithium is hard to detect. It exists in small amounts. It's an annoying transition. It's hard.
Right.
As we look in other wavelengths, there's going to be lines that are easy. There's going to be lines that are hard. And when we use these submillimeter and radio telescopes, instead of having all the colors of light, we have like 5
Mm-hmm.
wavelengths of one color.
Right.
So it's sort of like saying you have 5 of the 256 colors available to you. If you're lucky,
Right.
if you're lucky, you get that much. And so there may not be any strong lines in that. And there may not be enough data in that to have a lot of clear cut comparisons like you can get in optical spectra. So different wavelengths are harder and easier. If you want to see water, go use the infrared. Water is a pain in the infrared because it's everywhere you look. This is why
Right.
Sophia could find it on the moon and why we can't see water and other things from the surface of the planet because our atmosphere is filled with it. Other lines are harder. This is one of those lines that's harder. And one of the things I said when the detection was first made is we can't fully believe it until we see the spectral lines from other transitions in the phosphine molecule.
It's interesting because I assumed there was going to be some abiotic process that was producing the phosphine. Like if, there was these two pillars holding up this discovery, one being the detection of the phosphine, and there were some very good astronomers had worked on that. It had gone through 2 separate telescopes, the Clerk Maxwell and the ALMA, which is one of the most powerful telescopes on Earth. It had gone through peer review. And so it felt to me like the detection part was pretty solid. It was the methodology. I mean, it's never life. And so the methodology had to be like, it would have led to a really incredible discovery. Like, there's actually a lot more volcanism happening, or there's some methodology that there's some really interesting upswelling from the surface of Venus to the high atmosphere that's really fascinating, or something like that. There would have been some abiotic method that would have been figured out that would have been really exciting. And I would have put, if you gave me $100 to bet on which one of those was more likely, I would have put 90% on abiotic method, 10% on problem with the data in the first place, and yet here we are with the data being the thing that's actually the part that's getting. But when you look back at all of the times that
is a common problem.
This is the problem. Yeah.
Yeah.
When you think about the ALH, the meteorite, the Allen Hills meteorite, it was bad data. when you look at the
The cosmic microwave background Beppo-Sachs polarity measurement.
when you look at the primordial gravitational waves,
Yeah.
when you look at the the arsenic-based life, each one of these, it actually, in the end, it turned out to be that the original data were wrong. And I think that that's kind of fascinating that, and you know, I mean, I gotta give a huge shout out to Paul Sutter for this, because he has just a quote that just resonates so beautifully. He says, if it's interesting, it's probably wrong. And that is just a beautiful guide.
And here I just want to caution, it wasn't the data that was wrong, it was the processing of the data. The telescope's going to detect whatever the universe
Right. Yeah, of
has to
course.
send our direction, and then humans have the ability to completely screw stuff up.
Yeah.
And so data is whatever it's going to be, and we just screwed up in our analysis of it.
Yes. But and that clearly, it's like the more interesting. I mean, it's funny. I mean, I think, you know, if you could go back and say, like, what did they do wrong?
They believed that people at Alma knew how to reduce their data.
Well, sure. Yeah. I mean, I guess that's it, is that they should have said, we detected phosphine. I guess, you know, like, was it that phosphine potentially being an abiotic thing that shouldn't be on Venus is such an exciting, you know, it's like alien megastructures, right? You know, we see a weird thing around Tabby Star. We don't know what it is. And people go, could it be an alien megastructure? And you're like,
Maybe, but we need to do more research.
Yeah, I mean, we can't rule it out. Then you're saying alien megastructures? You know? No.
So the team was really good about saying we have not detected life. We have detected a atomic line consistent with phosphine. We have ruled out this one other molecule that we thought it could be. And more data is needed. And all the rest of us who were full of hope for something that was goodness and light in 2020, we're like, let it be life.
Yeah.
And this isn't to say we've ruled out the possibility of life. This is to say, yeah.
Yeah, I mean, I think we're on the road to ruling out the possibility of life. Like, I think, you know, if the, you know, of those two legs to that ladder of life that I mentioned, the detection and the abiotic method for doing it, you kick out the strong one, the other one goes too. So I think at this point, you know, I think we're going to say goodbye to the potential discovery of life on Venus. Right. Uncle Willie's saying in the FTL neutrino stream was a bad connector. Yeah, neutrinos don't go faster than light.
Yeah.
Same problem.
Yeah, that I was thinking of that one.
Yeah, that's another
just
good
forgot
example.
Who had that. There was a loose connector.
Yeah.
And the difference in distance that introduced to the system screwed up the results.
Yeah, and so it's almost like your enthusiasm for the discovery needs to be inversely proportional to your excitement, or to your belief that it's true needs to be inversely proportional to your excitement for the result. Like the EM drive. Come on. There's no way that that's a thing. It's a mistake. But, you know, faster than, you know, a spacecraft that would allow you, you know, non-inertial travel. That would be the best. That would be great, but it probably doesn't work. Wah, wah.
I'd settle for tardigrades, like on another world. That's all I want.
Yeah.
Just tardigrades.
All right. Well, we've reached the end of our hour. Pamela, thank you so much for bringing your brain. Everybody watching us today, we really appreciate it. Thanks to all of the moderators. Thanks to Nancy for helping organize. Thanks to Richard for doing the editing and putting up with our file size shenanigans. Pamela, what are you working on right now that people should be checking out?
Next week, we are going to be doing a massive digital house cleaning because what else do you do when stressed out? And so stay tuned for the launch of new content over on CosmoQuest. And there's also grant writing going on in the background. So expect much whining about having to do budgets.
We will try again to do a star party on Saturday night. At this point, I don't know. Stay tuned, everybody. We'll see what happens. All right. Thanks, everyone. Thanks, Pamela. And we'll see you all next week.
Bye-bye.